The Navier Stokes equations are the mathematical foundation used to describe how fluids flow. From ocean currents to the airflow over an airplane wing, these differential equations govern the dynamics of all viscous substances. When a fluid becomes turbulent, energy cascades. It transfers from large macroscopic eddies down to progressively smaller microscopic scales. The mathematics contain a specific vulnerability. In the theoretical limit of zero viscosity, the equations lack a built-in mechanism to halt this downward energy cascade. Without a mathematical stopping point, the energy continues to compress. The equations allow the fluid's energy density to approach infinity in a finite amount of time, creating a mathematical singularity. This mathematical flaw is the core of the Navier Stokes existence and smoothness problem. Classical physics cannot prove these equations always yield smooth solutions because the model lacks a physical regularizer to arrest the cascade at arbitrary scales. Classical thermodynamics defines thermal diffusivity and kinematic viscosity as passive material constants. They describe how fast heat or momentum spreads through a specific substance. This diagram isolates their shared dimensional signature. Both thermal diffusivity, denoted as alpha, and kinematic viscosity, denoted as nu, carry the exact same dimensions, length squared per unit time. Length squared per time describes an areal sweep rate. This specific geometric signature does not appear anywhere else in classical physics as an independent base quantity. The space-time occupancy, or STO framework, approaches this signature differently. It proposes that this unit combination is not a passive material property, but an active geometric operator called the angler. The angler is the exact geometric rate at which a physical system resolves spatial curvature into temporal structure. Redefining this dimensional signature as an active geometric conversion rate provides the exact physical regularizer missing from the Navier Stokes equations. This equation models heat distribution. The Laplacian operator measures spatial concavity, boxed as spatial curvature. The time derivative is temporal evolution. The alpha symbol bridges them, functioning mathematically to convert that spatial curvature directly into a rate of temporal change. To prove thermal properties are geometric, we use the STO neutrality transform. This mathematical operation inextricably links thermal behavior to mechanical force. At water's triple point, a state of maximal equilibrium, thermal conductivity and saturation vapor pressure share identical numerical values once SI units are removed. Applying a transform operator carrying the angler's dimensions converts the spatial boundaries of pressure directly into the temporal boundaries of conductivity. At a state of maximal neutrality, thermal properties and mechanical pressure are revealed to be interchangeable geometric projections of the exact same underlying energy field. The STO metrology axiom places a hard threshold precisely at 0.1 millimeters. Below this subledger regime, thermal gradients instantly dissipate as random entropy. Above it, in the superledger regime, spatial energy gradients persist, plotting their curvature onto a macroscopic structured ledger. Because the material cannot manage the persistent gradient itself, the excess energy is offloaded into the geometric structure of the surrounding reference frame. Above 0.1 millimeters, diffusivity isn't a passive material property. It becomes an active frame operator, processing spatial curvature into stored temporal information. In the classical fluid cascade, energy has exactly two pathways: spatial advection, moving within the fluid, and viscous dissipation, converting to heat. The STO framework introduces a third pathway for fluid dynamics: temporal containment. Kinematic viscosity functions as the momentum equivalent of the angler. When the turbulent cascade crosses the 0.1 millimeter boundary, this operator activates. This is the augmented energy balance equation. It includes the classical inputs and outputs, but adds a new term, highlighted here: the temporal absorption rate. This temporal absorption rate is defined by the Landauer limit, the minimum theoretical energy cost required to write or erase a single bit of information. Reaching the resolution limit, energy that cannot be advected or dissipated is absorbed geometrically. The spatial gradient is converted into temporal structure, creating a finite energy sink. This Tazel-augmented Navier Stokes equation formally integrates the temporal absorption rate into the classical model. Isolating the effective viscosity term reveals it's the sum of classical kinematic viscosity and a new temporal curvature viscosity, driven by local strain rate energy and spatial curvature. When spatial curvature is low, the temporal curvature viscosity calculates to zero. The equation perfectly reverts to classical Navier Stokes dynamics. When spatial curvature spikes exponentially toward a singularity, the temporal curvature viscosity rises proportionally. The intense curvature flattens out into a smooth, stable wave structure to absorb the excess energy. This pointwise regularizer mathematically guarantees global existence and smoothness. It prevents infinite blowup through rigorous thermodynamic accounting, avoiding the need for arbitrary mathematical bounds. The space-time occupancy framework's resolution to the Navier Stokes problem is strictly falsifiable through physical experiment. First, physical measurements of diffusivity will shift their behavior. Exactly at the 0.1 mm boundary, diffusivity will transition from a strict material constant to exhibiting observable, frame-dependent effects. Second, this data plot illustrates the turbulent flow energy spectrum. The framework predicts that the temporal absorption mechanism will produce a quantifiable anomalous spectral shoulder, deviating cleanly from the classical cascade curve. This redefines thermal and momentum transport across physics. Heat conduction and viscous smoothing are no longer modeled strictly as random molecular motion. The smoothing out of macroscopic gradients is a curvature-driven transfer of information. It is the geometric mechanism by which spacetime writes the physical spatial present into the structured temporal past.